Have you ever wondered why we wear light colors in the summer and dark clothes in the winter? Or how a thermos keeps your coffee piping hot for hours? You know, we feel hot and cold every single day, but the actual science behind it? Well, it's way more interesting than you might think. So let's pull back the curtain and uncover the secrets of how heat really works.
First things first, let's tackle a huge misconception. We trust our sense of touch, right? It tells us if something is hot or cold. But what if I told you that you can't always trust it? In fact, your own hands can lie to you, and I'm about to show you exactly how with a super simple experiment.
Okay, here's how you can try this at home. You just need 3 bowls. In one, you put some cold water. In another, some hot water. Not boiling, but definitely hot. Now go ahead and stick one hand in the cold water and the other in the hot. Now you just have to wait for a minute or two. Let them soak. What's actually happening here is that the nerves in your hands are getting used to these temperatures. They're adapting. Your hand in the cold water is adjusting to cold, and the other one is getting used to the heat. All right, now for the wild part. That third bowl has just lukewarm, room temperature water in it. On the count of 3, you're going to take both hands out of the hot and cold water and plunge them into this middle bowl at the exact same time. Ready? And this is where your brain gets totally confused. The hand that was in the cold water is now screaming, "This is hot." But the hand that was in the hot water is telling you the exact same water is cold. So you've got 2 hands in one bowl of water sending 2 completely different signals. What's the takeaway? Our sense of touch is relative. It can absolutely be fooled. So that's our first big lesson. Our hands are, well, they're unreliable narrators. They don't actually measure temperature. What they're really wired to do is detect the change in heat. Your cold hand feels heat rushing in from the lukewarm water, so it registers that as hot. Meanwhile, your hot hand is losing heat to the water, so it sends the signal for cold. Okay, so if our hands can't give us the real story, what can? We obviously need a tool that isn't so easily tricked. We need a way to find out the objective truth about how hot or cold something is. And that reliable measure is what we call temperature. It's a number, a specific value that tells us exactly how hot or cold something is, no feelings involved. And the device we use to get that number is, of course, the thermometer. You've probably seen one of these a million times. This is the clinical thermometer. It's a very specialized tool, designed for pretty much one job and one job only, measuring the temperature of the human body. Now, most thermometers work on a really simple principle called thermal expansion. Basically, as the liquid inside gets warmer, it expands and creeps up the tube. But clinical and lab thermometers are built for very different things. The clinical one on the left has a really narrow range, right? Usually 35 to 42 degrees Celsius, because our body temperature doesn't fluctuate that much. A lab thermometer, on the other hand, needs to be ready for anything. It has this huge range, from -10 all the way up to 110 Celsius, so it can measure everything from ice water to boiling water. But this brings up a really interesting question. Have you ever noticed how with a clinical thermometer, you can take it out of your mouth and the reading just stays put? But if you pull a lab thermometer out of a beaker of hot water, that liquid level drops like a rock. What's going on there? The secret is this brilliant, tiny little piece of engineering. See that little bend in the glass tube right above the bulb? It's called a constriction, or a kink, and it acts like a one-way gate. It lets the mercury expand upwards, but it physically stops it from falling back down on its own. It locks in the highest temperature reading, giving you time to actually read it. So clever, right? Okay, so now we can reliably measure temperature. Awesome. But that just brings us to the next big mystery. How does heat actually get from one place to another? It turns out heat has 3 main ways of moving around. Let's call them its 3 secret moves. But before we get into those 3 moves, we have to know the one unbreakable golden rule of heat. And it's this: heat always, and I mean always, flows from a hotter object to a colder one. It's a one-way street. This is why your hot coffee eventually gets cold, and your cold drink eventually gets warm. No exceptions. All right, heat's first move, conduction. This is basically heat transfer through direct touch. Think of it like a line of dominoes. You push the first one, and the energy gets passed all the way down the line, but the dominoes themselves don't actually travel. This is how heat generally moves through solid objects. This little experiment shows conduction perfectly. You heat one end of a metal rod with a candle. The heat then travels, or conducts, along the rod, and as it reaches each little piece of wax, the wax melts and drops off, one by one, in perfect sequence. This is the exact same reason the handle of a metal spoon gets hot when you leave it sitting in a mug of hot tea.
Now, some materials are way better at this than others. Things that let heat pass through easily, like most metals, we call conductors, and things that are really bad at it, like wood, plastic, or even air, we call insulators. And this is why your cooking pan is made of metal, to conduct heat to your food, but the handle is plastic or wood to insulate your hand from the heat.
Okay, on to heat's second move, convection. This is the main way heat travels through things that can flow, like liquids and gases. The key thing to remember here is that the substance itself actually moves, carrying the heat along with it. And the simple rule is this: hot stuff rises and cool stuff sinks.
It's usually hard to see air or water moving around, but this experiment makes the invisible visible. See that little colored crystal at the bottom of the flask? As you heat the water, you can actually see the hot colored water rising up. The cooler water from the top then sinks down to take its place, gets heated up, and rises too. This creates a circular flow, a convection current, that eventually heats up all the water in the flask.
And this doesn't just happen in a little flask, it happens on a massive global scale. Think about the beach. During the day, the land heats up much faster than the sea, so the air over the land gets hot and rises. To fill that space, cooler air from over the sea rushes in. That's a sea breeze. Then, at night, the whole thing reverses. The land cools down faster, so cool air flows from the land out to the sea. A land breeze. It's just a giant convection current.
And that brings us to heat's third and final move, radiation. Now this one's a bit of a game changer. It doesn't need any stuff, no solids, liquids, or gases to travel through. It can move right through the empty vacuum of space. This is how we feel the warmth of the sun, even though it's 93 million miles away. And it's how you can feel the heat from a campfire, even if you're not touching the flames or in the path of the rising hot air.
So, we've got our three methods: conduction, convection, and radiation. We know how to measure heat, and we know the golden rule it always follows. So now, let's bring it all home and apply this science to solve that everyday mystery: why we wear the clothes we do. This super simple experiment tells you almost everything you need to know. Just take two identical cans, one painted black and one white, and fill them both with water. Then, leave them out in the sun for a while. When you check them later, the water in the black can will be much warmer. Why? It's all about radiation. Dark surfaces are fantastic at absorbing radiant heat, while light surfaces are great at reflecting it away. And that right there solves our clothing puzzle. In the summer, we wear light-colored clothes to reflect the sun's radiation and help us stay cooler. In the winter, we wear dark-colored clothes to absorb as much of that precious solar heat as we can. And what about a woolly sweater? Well, wool is a great insulator for two reasons. First, the fibers themselves are poor conductors of heat, but the real magic is that they trap tons of tiny pockets of air. And since air is a fantastic insulator, that trapped air keeps your own body heat from escaping. So the next time you get dressed in the morning, you can think to yourself, what laws of physics am I putting on today?